The objectives of this video is to define crystalline solid, explain the crystal structure of diamond, describe the properties and application of diamond, and describe the crystallization of diamond.
Assalamualaikum and hi. Today I want to introduce about crystalline solids. What are crystalline solids? Crystalline solids are materials in which atoms, ions or molecules are arranged in a highly ordered, repeating pattern that extending throughout the material. This regular arrangement results in a crystal lattice, a framework that detects the solid's physical and chemical properties. Unlike amorphous solids, where atoms or molecules are arranged irregularly, crystalline solids exhibit a structure organization that is uniform and periodic. Next, we move to the characteristic of crystalline solids. Firstly, crystalline solids possess a definite melting point. Unlike amorphous solids, crystalline solids exhibit a sharp distinct melting point. This is due to the uniform energy required to overcome the consistent interatomic forces throughout the crystal structure. Secondly, crystalline solids exhibit anisotropic properties, where the crystals often display anisotropy, meaning their physical characteristics such as electrical conductivity, optical properties, or mechanical strength vary depending on the direction along which they are measured within the crystal. And lastly, crystalline solids demonstrate a high structural stability, the robust and highly organized arrangement of atoms that held together by a strong covalent or ionic bonds that ensures exceptional structural integrity. This leads to materials with impressive rigidity and durability, like the unyielding nature of diamond. Moreover, diamond is an exemplary model of a covalent network crystalline solid. Firstly, diamond consists entirely of carbon atoms and is an allotrope of carbon alongside graphite. Despite having the same elemental composition, diamond and graphite differ significantly in their atomic arrangement and properties. Secondly, each carbon atom in diamond is sp3 hybridized and forms 4 strong covalent bonds that arrange in a tetrahedral geometry. This bonding pattern extends continuously throughout the structure. Thirdly, diamond forms a three-dimensional diamond cubic lattice in which tetrahedral units are linked together to create a rigid and continuous network. As a result of this extensive covalent bonding, diamond exhibits exceptional hardness and is the hardest naturally occurring material, with a value of 10 on the Mohd scale. This property accounts for its widespread use in cutting and drilling tools. And lastly, in addition, diamond has extremely high thermal conductivity, making it an effective heat sink in electronic applications. However, it functions as an electrical insulator, as all valence electrons are localized within covalent bonds that preventing electrical conduction.
This slide shows the comparison between crystalline solids and amorphous solids. First, in terms of atomic arrangement, crystalline solids have a highly ordered and repeating lattice structure, while amorphous solids have a random and disordered arrangement of particles. Next, for shape, crystalline solids have a definite geometric shape, whereas amorphous solids have irregular shape. When we look at the melting point, crystalline solids have a sharp and well-defined melting point. In contrast, amorphous solids do not melt at a single temperature, but soften over a range of temperature. For physical properties, crystalline solids are anisotropic, meaning their properties vary with direction. Amorphous solids are isotropic, so their properties are the same in all directions. Finally, examples of crystalline solids include diamond, sodium chloride, and quartz, while examples of amorphous solids are glass, rubber, and plastic.
Diamond has a giant covalent structure where each carbon atom undergoes sp3 hybridization. One s orbital plus 3 p orbitals meets to form 4 sp3 orbitals. These 4 orbitals form 4 strong sigma bonds with 4 neighboring carbon atoms. These bonds are arranged in a tetrahedral shape. Diamond forms a three-dimensional rigid lattice that goes throughout the entire diamond but not as separate molecules. These covalent bonds make diamonds extremely hard. It has been used as a cutting tool for glass. It has no free electrons, thus diamond cannot conduct electricity. Light can pass through the lattice, which makes diamonds transparent.
Natural crystallization of diamond. Natural diamond is formed deep within the Earth's upper mantle, about 140 to 200 kilometers below the surface. This process requires extreme conditions with temperatures between 900 and 1400 degrees Celsius and pressures of around 5 to 6 gigapascals. Under this high pressure, carbon atoms arrange themselves into a stable sp3 tetrahedral crystal lattice which allows diamond to form. Diamonds are brought closer to the surface through kimberlite eruptions. These are violent gas-charged volcanic events that form small volcanic pipes, dikes, and seals. Kimberlite pipes usually have a carrot-shaped structure and consist of three main zones: the crater zone near the surface, the diatreme zone, and the root zone, which includes dike and seal at depth. During the eruptions, diamonds are carried rapidly upward, preventing them from transforming into graphite. Synthetic crystallization of diamond. Synthetic diamond can be formed using two main methods. The first method is high pressure, high temperature HPHT. This method mimics the mental condition of natural diamond formation. It uses graphite, a metal catalyst, and a diamond seed. Under high pressure and high temperature, carbon crystallizes into diamond. This method is commonly used for industrial diamonds and gem quality diamonds. The second method is chemical vapor deposition, CVD. In this process, a carbon-containing gas, such as methane, decomposes into carbon radicals. These carbon atoms then deposit layer by layer onto a substrate. This method allows precise control over purity, thickness, and crystal quality, and it is widely used in electronics and advanced technological applications.
On this slide, it shows the properties of diamond. First, in terms of hardness, diamond is extremely hard. It is the hardest natural substance because each carbon atom is strongly bonded to 4 other carbon atoms. Next, the melting point of diamond is very high, which is above 3,500 degrees Celsius. This is due to the strong covalent bond in its structure. For electrical conductivity, diamond does not conduct electricity because it has no free electron available to carry electric charge. However, diamond has excellent thermal conductivity, meaning it is very good at conducting heat. In terms of optical transparency, diamond is highly transparent, which allows light to pass through easily and give it brilliant appearance. Diamond also has a very high strength due to its strong covalent bonding network. Lastly, although diamond is very hard, it is also brittle, meaning it can break or shatter if a strong force is applied in a certain direction.
Next, we go to the application of diamond. On this slide, we would like to explain the application of diamond, focusing on how its unique properties make it very useful in both industry and jewelry. On the left side, we see how diamonds are used in cutting and drilling tools. Diamond is the hardest natural material, which make it ideal for cutting very tough material like metal, glass, ceramics, rock, and concrete. Diamond-tipped tools are commonly used in mining, construction, and oil drilling because they can withstand extreme pressure and wear. This increases efficiency and also extend tool life, saving time and cost in industrial work. On the right, diamonds are used in jewelry. Diamonds are highly valued because of their brilliance, transparency, and sparkle. Their high refractive index and dispersion allow light to reflect and split into colors, creating their famous shine. In addition, diamonds are stretch resistant, which make them perfect for long-lasting ornaments such as rings and necklaces. So, even though these applications are very different, both rely on the same key properties of diamond, which is hardness, durability, and optical brilliance. This slide shows how diamonds are used in advanced technology, especially in electronic and optical systems. On the left, diamonds are used in electronics as heat sink. Diamond has the highest thermal conductivity of any non-material, which means it can transfer heat very efficiently. In high-power electronic devices such as semiconductors, lasers, diodes, and microwave components, excess heat can damage the system. Diamond helps by removing heat quickly, preventing overheating and improving both performance and lifespan of the device. On the right, diamonds are used in optical devices and lasers. Diamonds are transparent over a wide range of wavelengths, from ultraviolet to infrared. Because of their resistance to heat and radiation, diamonds are ideal for high-power laser windows, lenses, scientific instruments, medical lasers, and even space optics. In both electronics and optics, diamonds are used because they can handle extreme conditions, such as high heat, high energy, and radiation. Therefore, diamonds are not just gemstones, but also critical materials in modern technology and science. In conclusion, diamond is a crystalline solid with a highly ordered and repeating atomic structure. In diamond, each carbon atom is bonded to 4 other carbon atoms in a strong 3-dimensional network, which gives diamonds its exceptional strength and stability. This unique structure is responsible for its important properties, including extreme hardness, a very high melting point, electrical insulating behavior, excellent thermal conductivity, and optical transparency. Diamonds can form naturally deep inside the Earth's mantle under very high pressure and temperature over a long period of time, and they are brought to the surface by a volcanic eruption. Diamond can also be produced artificially using high pressure, high temperature HPHT and chemical vapor deposition CVD methods, which imitate natural formation conditions in a controlled environment. Because of its outstanding properties, diamond is widely used in cutting and drilling tools, jewelry, electronic heat sink, and optical devices. Overall, diamonds demonstrates how crystal structure and crystallization condition directly influence a material's properties and application.